And now we are recording. And as we always do, we begin with a review. Do you have questions?
Yeah, I actually have a number of questions.
Excellent.
So I guess I was looking at your GitHub with like talking about converting from C to assembly, and there were a few commands in assembly that I was a little confused about how they worked. Like one of them was STP. Like there's brackets and there's this exclamation mark, and I couldn't quite figure it out with Google what it was doing.
Okay.
I know it's storing pairs, but that's all I know.
Did you try looking at the reference material that was also given to you? Or is it Google was the place you went?
Well, I was looking at the reference material, like the if statements and stuff, like you're talking about that reference material. Yeah, that's why I understood everything else basically.
Okay.
The STP
Good.
was.
All right, well, let's take a look at some things first, all right? I've started my screen share, so where is it? There it is. Okay. All right. Only a small number of instructions can touch RAM. Okay. RAM stands for random access memory, and it's what you think of when you think of main memory. Okay, so you have some number of gigabytes of main memory. Real programmers can do amazing things with 4K kilobytes of memory, but don't get me started.
We're not real programmers, at least not yet.
Yeah. Okay. So let's just first draw a picture of how these things lay out in the hardware. So you've heard of a CPU, central processing unit, and you've heard of RAM, and you've heard of disk. Okay. So there are actually things in between the CPU and the RAM. Okay, this is your main memory. So this is like, let's say on my machine, 16 or 32 gigabytes. Now it turns out there are certain memory locations that are built right onto the CPU. Those are the registers. Okay, so we've been learning about registers. We know that there's X0 through X30, and we know that the X registers are the same physical locations as the W registers. Let's just go up to 29 there. Okay. Now, by same physical location, the only thing different between an X0 and W0 is W is 32 bits wide, where X is 64 bits wide. If you read from a W register, you get the first 32 bits of an X, the same number to X register. If you write to a W register, you can only write up to 32 bits, and the other 32 bits in the same X register will be blanketed to 0. Okay, now these are blindingly fast. So access to these kind of storage locations is unbelievably fast. This is going to be less than 1 nanosecond. Now RAM, on the other hand, is on the order of microseconds. So that's 100 times slower. Disk, on the other hand, is on the order of milliseconds. So that's another that's 1,000 times slower than RAM. RAM's 1,000 times slower than the CPU registers. Okay. Now, Whenever you have items, whenever you have storage devices that are of vastly different speed, a computer scientist would add a type of abstraction called a cache. So here, in between RAM and the CPU is one or more layers of cache. Typically on modern computers, there might be 3 layers of cache, an L1, an L2, maybe even an L3. So this one is tiny, this one is medium sized, and this one is big, comparatively speaking. So L1 cache, there might be on the order of a megabyte, 1,000,000 bytes. L2, there will be more, and L3, larger still. Now, talking about, so this is size. And now let's talk about speed. So this is super fast, perhaps only 10 times slower than the register. This one is medium, and this one is the slowest of the 3 caches, but still far faster than RAM. So the general picture here is among the caches. In fact, for all of these storage devices, the faster it is, the smaller number of them you get. So the fastest of all is the machine registers. Those are on the CPU chip. They are built into the hardwired logic of the CPU. You only get a few of them, unbelievably fast. Then the L1 cache is super fast, but not very big. As you go from L1 to L2 to L3, the caches get larger, but slower. By the time you get to RAM, it is very, very, very big, but extremely slow. And then beyond that, to the disk drive, a persistent storage device will be far larger, terabytes in size, potentially, and also far slower. Okay, so as a difference of 1,000 to get from milliseconds to microseconds, difference of 1,000 to get from microseconds to nanoseconds. So that makes a register, what, 1,000,000 times faster than a disk drive? Okay, so question you probably want to ask is, what is a cache? A cache is some type of intermediate location that is faster, but on the other hand, smaller than some other storage device. It is in a pizza store, somebody stands there folding boxes and puts the folded empty boxes in a stack. That is a cache of empty boxes. The reason for doing that is so that as pizzas come out of the oven, they go right into a ready-made box and delivered to the customer. So that's what caches are all about. Now, when something is read from the cache, when something is read from RAM, it will percolate, unless you do something extraordinary, it will percolate through all the levels of the cache until finally it gets to the CPU. So this is just a quick digression. If you refer to RAM address N, and that would be with perhaps an LDR, LDP, and STR, STP instruction. These are the instructions you have that will read from and write to memory. And you want to use address N, and N hasn't been used before. So it will have to, the CPU will look at L1 cache, say, do you have the contents of address N? No? Okay. L2, do you have the contents of address N? No. Go to L3. Do you have the contents of address N. No, shit, I gotta go all the way out to RAM. And that's gonna take a long time. So the value from address N in RAM is then put in the L3, put in the L2, put in the L1, and finally the LDR or STR, depending on which instruction you're doing, gets to execute. Now, what about if very, very, very soon after this, you want the contents of address N again? CPU says, hey, L1, do you have N? L1 says, yeah, I have the contents of address N, here it is. So instead of taking 1,000 times longer than a register access, this only took 10 times longer than a register access. So fantastically big win. Caches are good. Okay, that's why we have so many. But let's get back to this statement. Only a small number of instructions can actually touch RAM. The reason for that is the extraordinary difference in speed between the registers and memory. In the old days, you might be able to add 1 to a location in memory. And that's because the CPU is no faster than the locations in memory. But if we were to try to be able to do that now, our instructions would run 1,000 times slower than they might otherwise. So instead, we only have a small number of dedicated instructions. They are the only instructions that are actually able to talk to RAM. Okay? So those are the LDR and the LDP and the STR and the STP. So load, store, load register, store register, load a pair of registers, store a pair of registers.
Dr. Kvolitz,
Yeah.
is RAM access completely constant time?
Can you tell me a little bit more about your question?
So accessing any location in memory, is it constant time no matter which address I'm accessing?
Excluding the concept of a cache, let's say yes. So of course, if you introduce the concept of cache memory, then attempting to reference a memory address that's found in the cache will be lightning fast. Or I should say just much faster than attempting to access a RAM location that's not in the cache. Okay. Now, so we know LD stands for load something from memory. ST, store something to memory. That's all she wrote. There are some other instructions that do that, but we're not talking about them now. Now let's talk about the strange syntax that I believe it was it Joshua?
Yeah.
Saw the strange syntax and would like a better understanding of it. So an LDR and also the STR look like this. There's a register. Both of them take a register, comma, and then you need to treat another register as an address. Okay, so ADDR is an X register And it's only the X registers, not the Ws. So ADDR is an X register that contains an address.
So what do the brackets do?
I'm about to show you.
All right.
Okay, so if you had this int I, okay, you could also have int star pointer equals the address of I. Do we have any confusion about what I wrote? If you have this, then pointer has the address of the storage for I. And star PTR has the value of I.
What's the symbol that's next to the I in the pointer one?
Over here, so that's ampersand I semicolon.
Okay, thank you.
You're welcome. Okay, so this last line here, you haven't got any trouble with that, right? That's just your basic pointer. Okay, so now let's bring it back to the assembly language syntax and answer Jordan's question. The brackets is like this. Okay, so the pointer.
So we just like put in the pointer.
Could you say that again, Thomas?
We would basically just put in the pointer.
Yes, so let's say we have the following code. ADR, I'll skip the ADR, I don't want to, I'll bring it in later. So let's say that X6 has the address of I. To read the value of the variable I in memory would be an LDR into some register. Let's say you were trying to read along, 64-bit number. So let's say read it into X0 using X6 as the address. So the square brackets is a dereference of the address contained in the register inside the brackets.
Why do we load it into a different register instead of just reading it directly from the register?
Well, what's in the register, Jordan, is only an address. You need the brackets to say, go to memory at this address.
Yeah, that makes sense.
Now, Jordan does have a point, though, and this is an important point to make. I could also have said LDR X6, what's at X6. Now, the reason why I probably won't do that is that if I need to refer to X6 to I again, that means I need to go find its address again. So here's the important point that I'm making right now, and that is you as the assembly language programmer can decide what to keep in which register. And by making careful choices, you can make your code blindingly fast or very slow. So for instance, we'll look at a bunch of small assembly language programs today, and you won't see me reference memory for any local variables because I've designed these programs in such a way that the equivalent of the quote local variable, I'm just going to keep forever in a register. If you're working on something that was not trivial, you'll find that you have to occasionally bring something in to a register, use it for a while, and then store it back into memory. But as the programmer, let me repeat it, as the programmer, you get to decide what to use the registers for. And one of the things you want to do is, even though you have the concept of a local variable, you want to use the local variable only in a register because they're so fast. You don't actually want to make a local variable on the stack in memory.
Okay, I have another question.
Go ahead.
So, trying to read the documentation for LDR, I saw something about backwrite, I think. Is that what it is? So, like, you can automatically rewrite to the register, and I think you did that in one of your programs. I'm not sure I'm explaining it very well because I only kind of get what's happening.
Okay, so with your permission, Cephas, I'd like to respectfully ignore your question.
Thank you.
Yeah, see, but I said it really nicely.
Why are you ignoring my question?
Because I really want to stay focused on the material that I need to get across.
Okay.
Okay, now backwrite is a term I'm not familiar with, so I don't want to go near your question. Okay, now what you might mean is a write back cache, but let's just move on. I don't want to digress. So these two statements, in fact, well, just consider the second one to be trivia knowledge. This is essentially, so if X6 contained the address of I, then after executing this instruction, X0 would have the value of I. Okay? The reciprocal is STR, and let's say X2 into, we assume the address of I is still in X6. After this, I, which is in memory, would have the value in X2. So whatever digit numbers were in X2 would now be an I. So LDR for load, STR for store. Now, let's introduce the P versions. LDP, and that would be 3 operands. Register 1, register 2, and then something about the destination or source. In this case, it would be source. All right, so let me give you an example. LDP X0 and X1 from X6, from the location stored in X6. So this instruction would be the same as, let me write out some C code here. So it would be long star, well, instead of star, I'll use array notation. Okay, so there's an array of 13 longs. Okay, so now assume that X6 has the address of the array. So this instruction would put, now remember, these are longs, so A sub 0 would land in X0, and A sub 1 would land in X1. So the value of at offset 0 of the array would go into X0. So the LDP is a load of a pair of registers.
So where would the second the index of 2 be located? Would it be X2?
You know, this is a perfect time. No. This is a perfect time to add to your knowledge about those brackets. If you wanted to get and I have an example for you. So I'm not going to answer your question now, but when we look at the new example program I gave you called functions, in the functions directory, I'll remind you, Jordan, that was your question.
Okay.
Okay. So there's also STP, which is XN and XM, and then the XP, right? So go to the address contained in XP and get a pair of 64-bit values, put them in N and M.
So at your code that I'm looking at, you have two values inside those brackets. You have the stack pointers and -16.
Right.
So
Haven't gotten there yet.
oh, okay.
Okay. So far we've done this LDR, let's say into X0 from what is at X19. So X19 is the address in memory of something we want. And it's a 64-bit something. So I'm loading it into an X register, X0. Right. Now, let's say X19 has the address of this long array, right? Has the address of this long array. If I wanted array sub 1, watch this syntax, LDR into X0. Now I want the first, maybe this is a loop, right? Maybe I want the next member of the array. I could do this. X19 is the base address offset by 8 bytes. That is going to be exactly the same as A sub 1. Because it's an array of long. Every long is 8 bytes. Now notice there is no exclamation mark on the outside of the bracket. We haven't gotten to that yet, Joshua.
That's what I was
Show
talking
you a
about.
different example. Let's tie in some more knowledge. Let's say you have struct, and this is one of the examples that I've written for you. Struct, capital A, and it is a long num carrots. We're talking about the diamond ring that you got. And then it's also a float.
Excuse me, I just have a
Yeah.
brief question. So on that LDR, X register 0, comma, X register 19 offset by 8 bytes, would A1 be stored? It would only be one of them because it's a load of single register. So would A1 be stored?
Correct.
Okay.
Yes. Okay, so here's long number of carrots because it's billions and billions of carrots. Float size is the size of the ring. And that's it. Let's end there. Okay. So here's a struct. If I told you that, well, let's do this to bridge your understanding. So A, and here is a ring, right? And maybe you've got ring dot num carrots equals 6. You could also have A star pointer equals the address of ring. That's not news. You know you can do that. And then you could say pointer num carrots. And that's the same as this. It's the 6. Any problems so far? Okay, so what does this look like in assembly language? So you've got this struct called ring. It's in memory. It's a struct of type A, means it has 2 members, and you have one called ring, and it's in memory. So assume X19 has the address of ring. And one of the reasons why I don't keep Discord going is from time to time, it just decides to do stuff on its own, which I've just killed. Okay. So X19 has the address of a struct A called ring. And let's look at the structure. At what offset, based upon X19, at what offset is num carrots? So if X19 is the array, if X19 is the address of a struct ring, what is located at that address?
Wouldn't it be num carrots? Wouldn't num carrots
Exactly.
get 0?
Exactly. So the offset of this is 0. So I can get at a 64-bit value for num carrots, if X19 has the address of the ring, I would then say LDR into X0, let's say, of what's at X19. That will load the number of carrots into X0. It's equivalent to having written LDR X0 X19 comma 0. Now you see where I'm going. So this says add 0 to the contents of X19 and get along from there. Put it in X0. Now how would I get to size? First of all, the question is, what is the offset of size relative to the start of the struct?
Isn't it at the first register?
Okay, I heard an 8, which is the correct answer, and I heard something else.
I was talking about registers.
Okay, no, we're talking about the layout of a struct.
Okay.
So this long is consuming 8 bytes. So where does size start? At offset 8. Okay. So if I wanted to get the value of size into an X register, which by the way is an integer, not a float. So we'll learn about the floating registers later. It would be X19 comma 8. And it would not be into, no, that would be wrong. It would be a W register. And somebody tell me why.
ints are 32 bits?
Right, because floats are 32 bits long.
But
Well, so
technically
that's the first part of the syntax you need to know.
you could load it into an X register, right? It wouldn't be anything different.
No, it would be different. It would load the 4 bytes, including the float, and the 4 bytes next to it, which would be the wrong data.
Wait.
Oh,
Why would it load the 4 bytes next to it?
Because if
read
you, by
until-
specifying an X as a destination, that means pull 8 bytes. W as a destination pulls 4 bytes.
So wouldn't it only pull half of what's stored there?
Okay, let's take a look in memory. So let's say here's ring, right? And here it is. Hey, here it is in memory. And memory is 8 bytes wide in this picture. So at offset 0, you'll have num carets. And then at offset 8, you'll have size.
Did you say bytes or bits?
Bytes.
Okay.
This picture is 8 bytes wide. All right. Now let me finish the syntax for LDR and STR, and then we're going to go quickly to one of the more advanced examples. So far you've seen you can LDR or LDP or STR, SDP, some register, let's say X0, and then a bracket and another X reg. It has to be, this one has to be an X register. Okay, so that says X19 has an address. Go to that address in memory and retrieve 8 bytes to put in X0. If you had said LDR W0 X19, it would be the same explanation, except it would be 4 bytes because of the W. So that's what we've seen so far. Plus, we've seen that you can give an offset to the register, to the address. So you could say LDR, let's say W0 X19, comma 24. So this says X19 has an address. Non-destructively add 24 to that address and fetch 4 bytes. Okay, so the 24 is an offset.
So imagine, would this get really annoying and complicated when you have like, what is it called? Data structures that contain other ones? Like what if I had a struct inside of a struct? Because you can't store the whole struct in a register. You'd have to like keep on going down.
Right, you've got the address of a struct, and then a careful coding may mean that you can buffer up I'm answering the question a certain way. I want to make it more general. This is how you refer to memory. And if you have nested things, you can, by nesting, damn it, let me work it into this next example, but I still haven't gotten to the end of what I want to talk about. Let's add the other syntax that Joshua is seeing. So suppose you had LDR X0, so we're doing a long again, X19, and then 16 and an exclamation point. Okay, so this says add 16 to X19. So X19 has an address. Add 16 to that address, actually changing X19.
That's what I was referring to. I'm pretty sure that's called a write back or something in the document.
Okay, okay, good. So by adding the exclamation point, that says pre-increment or decrement. The difference between increment or decrement is whether, if this is negative, it's a decrement. If it's positive, it's an increment. So finally, there's another, if there is a pre-increment, there must be a post-increment. That would look like this, X19 by itself, comma, 16, outside the brackets. That's a post increment. Now, let's finally get to some code. What I want you to download and get ready to run. Well, first let's do some other refreshments.
Can I ask a question about that?
Yeah, go ahead.
So when you're talking about incrementing the address of X19, is the address of X19 rewritten to a different location in the register?
No, in place. It's rewritten in place in X19.
Locally, and then yeah, just for the command that you're writing. Okay.
Right.
It's rewritten.
Okay, so
to what?
what?
So like with the pre-increment, what it increments, I'm confused as what X19 changes to.
Okay. Now, let's say we had an array of char, because we'll learn a whole bunch of new stuff here. Let me change the share back to the iPad. All right, hello, where is it? Come on. Okay, so let's say you had char A16. Okay. And you wanted to print one letter at a time. Okay, so you might have a for loop for int I equals 0, semicolon, I less than 16, semicolon, I plus plus. And then you might have, I'll use the C way, print F, because you need to know how to do this, and double quotes, %C for character, comma, then A sub I. Okay? All right. So another way of expressing this would be to, and this is probably the way you would want to do it in assembly language. It's also the way that I need to do it in order to give the the demonstration to Jordan. So you'd have another one, say char star end is equal to A plus 16. So let's look at RAM now. And this picture of RAM is 1 byte wide. So here is the address of A, and you've got 16 bytes. So 0 through 15. This is offset of 0 from A. This is the offset of 15 from A. Now, where is end pointing to? End is pointing here. Do we all agree on that? Okay. So in this assembly language, suppose X19 has the address of the array, which, by the way, is just A. I didn't have to put in the address there. So I'm going to choose to use X20 as end above. So I would do this. I would first, given that I have X19, let's write all the code now. I have X19, and I'm going to add, putting the result in X20. Well, first, I need to move to X0. That's a scratch register. I put the value of 16 in there. I didn't need to do that. So X19 and X0. So this has 16 plus the address of A goes into X20.
And alternatively, couldn't you just do X20, X19, and then just 16, right?
Yes, you could have. Yep. Yeah, now I'm getting digressed here. You wanted to see what was being incremented. So let me just do it this way. It's getting. Okay, now you could have done it this way. While okay. So while the pointer is less than end, printf a single character and get it from star parenthesis PTR plus plus. Okay, this answers the question, what is it that's being incremented? So PTR is a pointer to char. Here's a post increment. So this syntax says, use PTR as a pointer and get a character. That's the character that'll be printed. And then add 1 to PTR. Do we agree? Okay, so if PTR was in some register, it would be an LDRB, and you have to put that into a W register. This says char. And to do this pointer increment, it would be, let's say, X19, comma 1, damn it, I don't want a Bezier curve. Exclamation point. So X19 is dereferenced. The byte is put into W0. Then 1 is added to it. And that is thanks to this syntax.
So the 1 is added to the address that is stored in X19.
Right.
Correct. Okay. And then what does the B stand for in the LDR instruction?
Okay. So if you want to get if you want to load 64 bits, it's going to be an LDR into an X register. If it's 32 bits, it's going to be an LDR. This is actually in the documentation I provided. It's going to be that to a W register. If you want to do a short, it's going to be an LDR half to a W register. And if you want to do a byte, it's an LDRB to a W register. This is all already online in the material that I've written for you. The same thing for STR. Okay, go to the class webpage, language concepts. Let's go directly to function calls because this will also be some questions that CFAS had. Let's take a look at f1.cpp. All right, so I'm going to write in assembly language a function that works with C++ and C, as it happens, that all it does is it takes it along. Notice it says int64, so that's going to be an X register. It takes along, doubles it, and returns it. Okay, that's all it does. Everybody got that?
Yes, Lord Helmet.
So F1 is the name of the function. The word extern means the code's not here. The code's in another file. And the word C says to the compiler that F1 is really the name of the function and disable, for the moment, name mangling. Now, name mangling is how C++ supports overloads. Okay, so what's this going to do? It's going to put 32 into V. And then it's going to print 32, and then the results of F1, which I claim will be 64. Okay? So let's take a look at the assembly language. So F1 CPP goes with F1A.S. Okay? So in order to make F1 visible to the linker, it has to be a global. And that's how it will link up with the extern from the C++ source code. So now it's important to understand the calling convention. So for Linux, this is not true on all OSs. On the ARM, first parameter goes in something zero.
Professor, are you supposed to be on the GitHub currently?
Right. I thank you for telling me. I switched to the iPad. Let me get some drinks on board here. Okay, so on Linux, on the ARM, the calling convention is the first parameter goes in some kind of register, 0. Maybe it's an X, maybe it's a W, maybe it's a floating point register. It depends on the type of the parameter. The second parameter, guess where it goes? Into something 1. Okay, 8th parameter goes into something 7. And then return values come back in X0 or W0 or float 0. So something 0.
So they would overwrite whatever's in the first parameter and stuff, or whatever's in
Correct.
your, okay.
And the computer automatically like chooses the best size, right? So like if the first parameter is a character, it's going to do W.
Correct. Yeah, the compiler will generate the correct assembly language. All right. All right, so everybody got that. On Linux, on the ARM, some register 0 gets the first parameter. If there's a second, it goes in something 1. If there's a third, it goes in something 2. So let's take a look
All the
at
way
this
to
code
8?
again. What's your question?
All the way to 8? Is that what you said?
All the way up to 7.
7, that looks like an 8.
Yeah, 8 values, 7 registers. I'm sorry, register number 7. It's also 8 registers. So here, take a look at this. Do you see the parameter getting passed? No, you don't. All you see is X0. That's the parameter. So this multiplies the parameter by 2, puts the results back in X0 and does a return.
Didn't you say that x0 assumes the first parameter of the function though, and in this, it's a sign? Well, never mind. X1 is just it's a nothing. Yeah.
Yeah, X1 is the value 2.
X0 is what's passed in, what's changed, and what's returned.
Right.
Okay.
Now, the next thing you need to understand about the calling convention is some registers you can count on being there, and some registers you can't if you call another function. So if your function calls another function, any other function, then some registers will be destroyed. Some will not.
How will we know which ones will or won't be destroyed?
I'm going to tell you.
All right.
Okay. So X0 through X7, these are always scratch registers. If you call another function, they will get destroyed. Okay, so X8 through let's call it 19, well, X18. And then X19 through X30. This is a little bit overboard. No, it's not overboard. If you use them, you must back them up and restore on exit of your function, exiting the function.
How would we do that?
You've seen many, many examples already in the sample code. That is the pushing them onto the stack and popping them off of the stack. And we'll see it more in a minute. Now these are if you need them, you must back up and restore when making function calls. Okay. So let's take a look at a little bit more complicated code, and I'll start pointing these things out.
I have one
All
quick
right.
question.
Yeah,
About
go ahead.
return. So does return always return the last modified register?
No, return doesn't return anything except changing the program counter, fetching the program counter from X30 and branching there. So the standard is your return value, if one exists, is in X0.
Okay.
Okay, let's take a look at this sample. And you can download all of these and try them on your ARM machine. Here, F2 is a function that is going to take an array pointer to shorts. You see how it's a short there? 16 bits. So it's an array of shorts. And it's going to take the length as a 32-bit, as an int. So L is going to be passed in what register, please?
0.
Good.
X0.
Not X0 though, W0. Why W?
Oh,
Because
32.
it's not 64 bits. Why 0? Because it's the first parameter. Now what will A be passed in? The address of A.
X1.
That will be in what register though? It is number 1, but is it a
Um,
W or an X?
X1.
It is an X because it's a pointer. And pointers are the same, it's a 64-bit machine. That means pointers are 64 bits. Okay, now notice it's a void. Now let's see what the assembly language looks like. F2.A, F2A. So this function is going to put a 0 into array 0, a 1 into an array 1, a 2 into array 2. You got it? It's putting the index into the array element at that index. Okay, so length comes in at W0 because it's 32 bits. Next register, next parameter. So array is going to come in at X1, and I'm going to use W2. Okay, this is ugly. So time for me to shift to an editor. Let me get one going. What computer am I on? Code will work. And all right, is this here and this here? And okay. Okay, so W0 has the length. So I put 0 in W2. Compare 0 to the length. And if I've reached the end of the loop, I go here to the return. So how do you know which way is which for the compare instruction? The compare instruction actually isn't a real instruction, if you want to know the truth. Instead, it's syntactic sugar layered over subtract. So what this is going to do is subtract the second argument from the first. So W0 will be subtracted from W2. And that will set certain condition bits. One of the condition bits is it larger than 0? Is it 0? Is it less than 0? Right? So if the length is 16, so 16 minus 0 is what? 0 minus 16, sorry. 0 minus 16 is what?
Yes. 16.
Negative 16, right? So is that greater than or equal to 0? No. So this is skipped. Now x1 has the value that points to the array. So use strh, which means 16 bits. Put the counter into the memory location specified by x1, then add 2 to x1. Then add 1 to the counter. And branch back to the
Sorry,
compare.
wait. So why why are we incrementing by 2?
Because it's the array holds 16-bit integers. The array holds 2-byte integers. So to get to the next one, we have to increment by 2. Finally, the void. Notice I'm executing a return instruction, but I didn't take any care at all to put something in x0. That's all that void means. Okay, so all right. Branch if the counter is greater than or equal to the length. Okay. So in fact, let me move this over here.
Oh, I have a question.
Yes.
So in the previous thing we did for iterating over a char,
Yeah.
you did a pre-increment. This time you did a post-increment, right?
Right.
So
That's correct.
why would we want a pre-increment before? Because wouldn't you miss the first one if you're doing a pre-increment? Because pre-increment is add something
Yeah,
to
but
the value.
this is a post increment.
Yes, but in the example you did last time, that was a pre-increment. So wouldn't we miss the first one if we're doing a pre-increment? Because pre-increment is add something to it, evaluate.
You're right.
So that this
Yeah,
one
so
was
that
wrong?
should have been a post also.
Okay.
Yeah, you're correct. Looking back at it. All right, so what does this do? This, okay, 2 bytes is a short at x1, then add 2 to x1. Add 1 to counter and loop again. Okay,
I'm actually still a little confused at the store. So why do we have W2 in the store half line?
store the counter as a short. Does that help? W2 is the counter.
So, okay, so you're putting W2 into X1 and then incrementing it by 2.
No, into the
So-
memory location specified by X1, then incrementing X1 by 2.
Okay. I think I get it.
It's here. There it is.
Yeah.
Also, what's the difference between saying 2F and 1B?
Okay, good. So assembly language, instead of using braces, you're using labels.
Mm-hmm.
So you're going to have to come up with a lot of labels. In fact, there's so many labels, but they all don't have to have meaningful words associated with them. So this is a label that I chose, F2. That means something. But many other labels, you just need temporary labels. So you can use digits. And when you go to branch to them, if you want to branch to one behind you, then it would be the digit 1 and behind. As opposed to, if you want to jump forward, it would be scan forward, find label 2, forward.
Okay, and I assume it'll just find the first 2. And then
In the forward direction or the backward direction, you could literally use the label 1 over and over and over again.
Terrible idea, but
Well, it's a terrible idea, but you could. That's what the F and the B is for.
okay. See,
All right,
this is what I needed. This makes so much more sense now.
good. All right, let's now look at F3. F3 is got the structs, okay? So here's a struct. It's got a long, an int, a short, and a char. So what I've shown you here is that the first member, called long, starts at offset 0. The int starts at offset 8 and goes on for 4 more bytes. That's why the short starts at 12 and goes on for 2 more bytes. So the char starts at 14. Okay? So what I'm going to do is design F3, which is going to dynamically allocate an S and fill it in, just like a constructor. Well, a lot like a constructor. Okay? So I have an S pointer, and it gets the memory allocated by F3, and then prints it out, and then frees the memory. So this is the same as delete. Does everybody understand what this program's supposed to do? Everybody. All right, so.
It just makes a thing to store, or does it just allocate things?
Yeah, so it allocates enough space to hold an S and then initializes it with certain values. Okay, let's take a look. So what this is going to do is dynamically allocate the memory for an S. And then it's going to initialize that memory with 64 will go in the long, 32 will go in the int, 16 will go in the short, and 8 will go in the char. Okay? Now, here's the first time we're doing this. So X30 is the link register. The link register is what's used to store where to return to when you call a function. So let's say main, and you call foo, and foo
We
calls
can't see your
bar.
drawing.
What?
We can't see your drawing.
Yeah, thank you. See, I did it right for one class period, and now I can't do it. Come on, why so slow? So here's main, and main calls foo, and foo calls bar. So at this point, X30 has something. When you call foo, X30 gets the next instruction, the address of the next instruction in main. So that when foo returns, it returns back to main. You know that. Nothing mysterious here. Inside foo, you call bar. X30 gets the address of the next instruction in foo. It overwrote X30. So unless you take care of X30, back it up and restore it, your return instructions will return to the wrong address and you'll crash.
So I would like if when I'm going from foo to bar, I would want to store whatever's currently in X30 in like X29 per se, and then when I go to bar, no. Okay.
Nope. You put that into memory on the stack.
Oh yeah.
So let's do this. Okay. So here's foo. And somewhere down here is the call to bar. Right? And here's main. And somewhere down here is the call to foo. So when you have a function that calls another function, and notice in the two previous examples I showed you, the functions that I wrote in assembly language didn't call any other functions. So I didn't have to save and preserve and restore X30. But now I am going to call malloc, which allocates memory. So I'm going to call, it means I'm calling a function inside my assembly language, F3. So that means I must protect X30. So to call foo is a BL to foo. Now the BL instruction is branch linked. So it does two things. One is it puts the next instruction address. Next instruction in X30. There's the overwriting. And then it branches to foo.
When you say branch, what exactly do you mean?
Go to.
Okay.
Branch. Okay, so here's your assembly language. And then you do a BL to foo. So that's going to put this address. Okay, it puts this address. That's the next instruction. It puts this address into X30 and then branches to foo. And at some point, there's a return. Now, how does that return know where to return to? It gets the return address from X30. And that means it comes back here and continues executing.
So let's say like before I call through, I allocate a little. I store the value 5, and then I go into foo, and then how would I get that value 5 if everything else is being overwritten? You know what I mean?
Okay, if you're passing it as a parameter, the 5 would be in one of the registers.
Okay, but if I don't, it would be overwritten, or it potentially could.
No, well, let's make sure that, let me finish this example. All right, and then we'll go on to your question. So the very first thing that foo needs to do is back up X30 on stack. Then the last thing it needs to do is restore X30 from stack. And then the return. Let's take a look at the code and I'll show it to you. There is the backing up of X30 onto the stack. So this says the current stack pointer, subtract 16 from it, then use that address to store the old value of X30. That's a push onto the stack.
Why minus 16?
That's a great question. This is a 64-bit machine, and that means addresses are 8 bytes. The ARM architecture demands and requires that the stack be manipulated only in multiples of twice the length of an address. So the length of an address is 8 bytes, twice that is 16. So when changing the value of the stack pointer, it has to be a multiple of 16.
What's the exclamation mark for? I forgot.
That is the pre-operation. So subtract 16 first from the stack pointer, then use it as a location.
Okay.
So I might have gotten confused with like bits and bytes, but so I thought we were going back. So it's going back 16 bytes and not 16 bits.
16 bytes.
Okay.
Right.
And for all those other brackets, are those also bytes and not bits?
These are all bytes.
Okay.
Okay. So let's go to the end of the function. So here's the backing up of X30. Here's the restoring of X30. So if you're writing a function, here's the whole function. If you're writing a function that includes any BL instructions, you must preserve X30 and restore it. Okay. So the definition of malloc is void star malloc length. So malloc, memory alloc, malloc, is the lower level means of allocating dynamically memory. So this says, I want 16 bytes. Now, wait a minute. How long is the struct? Is that the right length? Jordan, you say no. What's wrong?
There'd be 2 more. There's like the struct is what is it, 14 bytes?
Well, I'm using 8, 4 is 12. I'm using 2 more, that's 14, and I'm using 1 more, that's 15. So I see 15 bytes here Yet 15 is the wrong answer. It's 16 bytes long.
If you're allocating,
Because it can't measure anything except a multiple of 8.
It has to be, so everything has a natural alignment. And the size of a struct has a natural alignment of being a multiple of 8. So 15 is no good, but 16 is. So even though I'm using 15 bytes out of the 16, the length is still 16. Okay. So I put 16 into X0, which, by the way, to be perfectly correct, should have been W0, because no, it is an X0. Yep, it is an X0 because it's a size T, and that's a long, unsigned long.
So when you do mallocate, where do you specify the amount that you're trying to allocate?
Right here.
Oh, so when you call mallocate, it's going to take X0 as a parameter.
Exactly. That's what we talked about, right? The first parameter goes in the 0 register. The second parameter goes in the 1 register.
Is there a limit to how many parameters you can have?
No, but you're asking a good question. What if it's more than 8? And the answer is a different mechanism is used where the parameters themselves are pushed onto the stack. And the function you're calling has to know how to find them.
We should definitely do a barbecue this week.
Okay. All right. So look, here's the examples of all the different variations of STR. So an X register containing the value 64 is being written to 0 bytes away from the location returned by malloc. That's a underscore long. Then a 32 is being stored from the W1 register to 8 bytes away from the start of S, start of the structure. That's an int, right? Right. If I need to remember, if you need to remember what's what, there's the struct, and here's the assembly language. So here's how you store a 32-bit value. Here's how you store a 16-bit value, and here's how you store an 8-bit value. Now, what is this returning? What does this function return?
nothing.
Not true.
Wait, it doesn't?
What's in X0?
It's still 16?
No.
The struct?
Doesn't it return
Yes.
to the previous?
So
one?
at this point, after this, X0, this line and forward, X0 contains the address of the newly allocated struct. So that's its return value. So I simply do a return knowing that X0 already contains the correct return value. Okay. And check this out. I used assembly language to do a malloc. Where the heck did print come from? Well, the C++ compiler figured that out for me. Okay, any questions?
So like with project one, do you want us like I'm just confused. So we write the C file and the assembly file, but do we write the C file like what you're doing on the right, or do we write the C file as in we write the entire program in C and then we write everything in assembly as well, or just
Yes, so I give you a C++ program, right? Okay, so I'm asking you to write the C program, which is fully de-evolved, deconstructed. So that means the only braces you're allowed are at the beginning and ending of a function. So let me go, I'll do just a little bit of your work for you.
I mean, could you walk us through instead a hello world program, just to kind of show us actually writing assembly code and all that?
Okay, I've done it for some of you, but that's fair. All right, so this is going to be a complete hello world program, right? So, and I should demonstrate for you how to start up everything. That was also on my list of things to do. So let's go here. I'm in my home directory on a Mac, or you're in your home directory and on Wizzle. And I'm going to change directory to where I have all my virtual machine data. And then I'm going to say ARM using that alias. So this is my virtual machine starting. In a second window, this is also on my main machine, SSH user at localhost dash port number dash P 2222. And the password is A.
I don't think it's showing that second terminal window.
Son of a bitch, why not? All right, so apparently I have to click more than once. If I click on the one on the left, it shows the one on the right. And if I click on the one on the right, all right. All right, it's simply not showing this. Okay. And I'll just do it this way. I'll show the whole desktop. Okay. All right, so this is your virtual machine running. Leave it alone. Okay, so this is my SSH login. Let's take a look at what's here. There's some stuff here. I'm going to erase it all. All right, now there's nothing here. Now, in order to do the squirting of your work over to the virtual machine, you have to have this extension installed. And the way that you would do that is you could search SFTP, and the LixiMomo will be one of your choices. And the LixiMomo extension is the one I want you to use. Okay, so get rid of that. Now you have to have a directory open, a folder open. So I'm going to demonstrate that. I'm going to go back to, I'm going to create a folder, and let's call it Hello World, HW. I'm going to now go into Hello World, and I'm going to say Control Shift P, or On the Mac, it's going to be Control Command P. I guess, no, it's going to be Shift Command P. There it is. So Shift Control P on Windows and Shift Command P on the Mac. I'll type in SFTP and you'll see SFTP config. Click on that. Now you're setting up this folder to use the FTP plugin. The name doesn't matter. The host is correct at localhost. The protocol is correct at SFTP. The port number should be changed from 22 to 2222. The username is just user. And then put in, instead of slash, put in, let's say, the name of your project, in this case, HW. Go to the end of a line, new line, double quote, PASS, and select password, and fill in the letter A. Okay, save it. You can close it now. All right, so now I'm going to create a new file and let's see what happens because, all right, let's just create a new file. So new anything, and I'm going to save it as a .s. And I need to put it in the right directory, which is temp, and for me, and what I called it HW, right? Then I don't know where HW went.
Yeah, you called it HW.
You had it
what?
under function calls in
It's
language
not- okay.
concepts.
Foo and function calls, yeah, exactly.
TMP, language concepts, then HW.
Okay, good, all right. But where's HW?
Function calls. Function calls.
Okay, and
Then it's an
HW.
HW.
Wow, that's convoluted. But notice it says, oh man, look at the name of the file that I gave it. That's because I didn't fill one in. Let me delete that and start over. Delete. Okay, so here I'm going to create a new file and I'm going to save it as hw.s. And let's do this again and go find the right folder. Save. And it's done. It's down here. You see it says done. Now let's go look at the terminal. There's HW. And there's, oh boy, I totally screwed up. Let's see if we can find it. All of it got squirted down there to HW. Okay, so RM, okay. All right, so there's hw.s. So, okay, so dot text means you're about to write code. Dot align to means you want the code to begin on an even address. Dot global main means that this is the main function that the linker needs to be able to find. So it has to be global. So there's my symbol, my label, main. And we want this to be a hello world. I'll do it one way first. It'll only take a second. So I'm calling another function in this program. So that means I must do what with X30?
You must save it somewhere on the stack.
Good. So str X30 onto the stack. Got to manipulate the stack in multiples of 16 with that syntax. I can already go to the bottom and I can say LDR. Let's do the reciprocal. Okay, and then I could put in a return value. all this time you've been saying return 0 from main, right? So here's return 0 from main. Move into X0 because X0 is where the return values go, and use either put in a 0, or faster is to use the 0 register return. That is a functional program. Now let's get in .data. This says it's no longer code. Now it's global variables. These are your globals. So HW dot ASCII Z, that says null terminated C string. In this case, I'm going to use puts, so I don't need a new line. Then dot end, and nothing can come after the end. So in C, this would look like the following. It would look like this. Okay? So in assembly language, we've got to have some space in the global variables, some space for the text of hello world. That's down here in the data segment. So the address HW has an address. At byte HW is the capital H. So what I'm going to do is load the address into X0 of hello world, the label. And all I need to do is BL to puts, and this program is finished. I'm going to hit save. Done. So flip Windows, cat HW, there it is. GCC HW.S and A.out, hello world.
Wait,
All
what
right.
does puts do?
Puts, I expect that you will go read up on it. Okay, what does it do? If you have a constant string, like with no variable substitutions, you can use puts as a quick way.
Okay, so
All right.
how does it choose what it's outputting? Is it just going to go from X0?
X0, right, exactly.
Okay.
Now I'm going to change this program now. I'm going to change this instead to do this. Printf, hello world. And because printf, I have to have the new line character. All right, so I'm going to change it. There's actually no difference except for the new line.
So would you put the new line in the .asciz in data?
Yes. Okay, so this will now run. It'll be exactly the same thing. Hello world.
So
Now, before you leave, let me just say this. Before you leave, I've just run the program. Now say echo $? Whoops. Let me run the program again. Echo $? It's 0. So this is finally going to answer the question, when you return 0 from main, where does it go? So I'm going to come to the program, and I'm going to say, put 19 in there. Let's go back, compile it again, compile it again, run it again, and do that weird echo. 19.
What would you be using that echo command for?
Echo is part of the shell, and it just prints whatever you follows the word echo. The $? is the return shell variable for the return code of the previously run program. Okay, Now, go through the document that I've specified, and you'll be introduced at a high level to the different families of instructions. And that way, when you want to know how to do a move, how to do a multiply, you can just look in that document, okay? You now have, I am confident, every single one of you now knows enough, more than enough, to do the first project.
Nice.
Okay, but I'm still available to you for questions. We have to go now, I'm sorry.
Have a
See
good
ya.
day.